Okay, while we are waiting for your friends to hand in their homework, you can answer this question.
The velocity is constant. The velocity is constant.
Does it matter? Does it matter?
Buna gerek yok.
Yani teker teker sayfalar koyarsan kaybolma riskini de göze alıyorsun.
Yani şöyle
Benim için gerekli. Yani senin aldığın bir risk.
Bunları tek şıkkı yazıp yollamıyor mu?
Evet.
Ben
A, B diye.
hiçbir zaman şey yapamıyorum.
Bu onunla ilgili bir problem yok ama.
Neyle? Ha.
Bu senin iPhone'la ilgili.
Ne olabilir acaba? Ya öncekilerde de hiç olmamış.
Hı? Yani iPhone'un yollayamıyor. Orası kabul etmiyor falan diye bir şey değil burada.
Hocam ya benim ders kaydı daha yapılmadı.
Hı.
O yüzden ödevi alamadım.
Sen bana bir mail at.
Nasıl?
Yani durumunu anlatan bir mail at. Ben de kaydı bulunsun. Seni bu ödevden muaf tutarım en kötü ihtimalle. Ya da geç kabul ederim de.
Ben geç kabul etseniz daha iyi.
Ya onu çok tercih etmiyorum. Çünkü asistanlarınız çözecekler, dağıtacaklar. Muaf tutmayı tercih ederim.
Ben de zımbalamadım da ona.
Yani artık biraz geçti. Derse başlayacağız. Hadi.
Ona şey yap.
Hı? Okay, most of you have gotten the answer correct. I mean, basically, although they have the same speed, since their directions are different, they don't have the same velocity. So let's switch to another question. Now in this question you can assume that the cart is moving at constant velocity relative to Earth. Now we will have 3 assistants for this course, and I will send you an email about their contact information and names. 2 of them will be grading your homework. 1 of them will be doing recitation hours. And the time for the recitation hours will be announced in a couple of days. I mean, we will not be really asking you about at what time should we have the recitation, because since there are around 100 of you, I mean, I don't think we will be able to find a suitable date for all of you. So what we will do is we will have 2 recitations every week. So they will mainly be a repetition of the same thing. So you can either follow one or the other one. Okay, just a reminder for the newcomers. I mean, if you want to hand in your homework, you have to do it now, at the beginning of the lecture. I will not accept homeworks in the 2nd hour or the 3rd hour. Okay, so let's discuss this question a bit. Now, this time, although the majority has said A, there are a significant number of you who said B and C. So why A? So the question is, you're in a cart, which is open. You're just moving at constant velocity, and you're staying facing forward. So you throw an apple upward, vertically up. Where will it fall? In your back, in your front, or right where you are?
without air resistance, it should, we should meet after a while.
We should?
We should meet. Our car and Apple should meet in a few seconds later.
Okay.
But if there's an air resistance, let's say, towards and backward to us, and Apple have a velocity negative to our initial velocity, and they won't be, it's still behind, it will fall behind.
Okay, so you are saying that it's A. Okay, anybody else?
Well, I said A, but now that I think of it, it could be all of them, A, B, and C, because I think that A resistance depends on the shape of the objects. So if our car is like that and Apple is like that, the Apple will have more A resistance, so A will be true. But if it's other ways, and the answer changes.
So you are saying that it will depend on the... Right, but keep in mind the car is moving at constant velocity. It is C, so it will just fall down right at where you are. Okay. Mm-hmm. Okay, so I mean you are all answering to me, but you should discuss among yourself. So he says that it will fall behind. Can you convince him, or are you convinced by, let's say, her argument that it will fall right at where you are?
Yes, it's a projectile, and we should do it after a while. But for seeing our car with a 1 centimeter car, and it can be seen that if there's an air resistance, projectile motion won't be completed, and Apple stay behind of us. I can example of that.
Okay, so
if one is strong enough, for example, to negative velocity, our velocity, opposite direction. If it is strong enough, it will just go up and down. And we can say it won't have horizontal velocity. It will be balanced with wind.
So you are saying that if the wind is very strong, it will not have any horizontal velocity, it will just go up and down. Okay, so does it convince you that it will fall behind? Well, it's usually not advisable to change your reference frame. You just choose one and stick with it. Okay.
And the other is outside this system, this reference frame.
Now, you see, reference frame is something of our invention. So we choose a reference frame and we make our observations relative to that reference frame. It's not a property of the objects. It is something we choose. So even if the object is, you throw the apple upward, let's say, I mean, it doesn't have a different reference frame, or the reference frame is not something of the objects. It is our choice. We choose just one. And in fact, in this question, it's already, although it is not explicitly stated, it's said that there is a moving card. So motion with respect to which reference frame? So it's usually implied that it's with respect to the Earth. So this card is moving relative to Earth. You can stick to using the Earth as a reference frame fixed on Earth as your reference frame. both to describe the motion of the cart and also the apple, or you can choose another reference frame as you wish. But the cart and the apple, they don't have different reference frames. You just choose one to describe all the motion. Yes, any other explanations? Why A, B, or C? Well, because I told you that it is moving at constant velocity.
I think the wind is not important. If there is resistance, your vertical velocity of apple will decrease.
Okay.
So I choose it.
Okay.
Hocam aynı yere düşer. Yani C demek istiyorum. Çünkü yukarı doğru attığımız zaman vektör sadece şeyin hız vektörü oluyor, çarpım hız vektörü oluyor. Biz kendimiz ona ekstradan bir hız vektörü ekleniyoruz hocam. O yüzden yani havaya doğru hareketler bizle beraber bizim üstümüze düşer.
So your answer is, when we throw it, we are not adding a velocity vector. The velocity vector of the apple is the velocity vector of the cart. So it will just move up and down. It will just fall on top of us.
Hocam ben Adana diyorum. Neden? Çünkü arabada otururken elmayı yukarıya doğru attığımızda aslında elma havadan etkilenecek, rüzgardan etkilenecek. Neden? Çünkü arabanın kaportası yapısı bir havayı yarıyor, değil mi? Havayı yardığında rüzgar elimizi dışarı çıkardığımızda her zaman geriye doğru gidiyor. Elma da el gibi düşünürsek havaya attığımızda
I just want to correct one more thing. Do you know what cart is? It's not a car. It's not closed. It is open. So this is open. So just imagine you are sitting on a platform, open, the platform is moving, and so you just throw something upward.
But it is still given that it's moving with constant.
Yes. So you just stand on a platform, open air. The platform is moving relative to Earth at constant velocity, and you throw an apple upward.
It was an experiment. You put a boring ball in your nose, and it will never come back to your nose and hit. It's the same mechanic as that, because the air has a resistance and it pulls object in the other way.
Okay, pull the object in the other way.
Pulling, I mean opposite direction.
Okay. Sure. I mean, you are on off.
Why I think that while we're moving the car with the apple in our hand, the apple has the same velocity as us. But when we throw the apple's vertical velocity is the same as ours at the point where we make it. So taking air resistance into account, the vertical velocity of the apple will decrease. So as we keep moving, while the apple starts to fall down.
So how is the decrease in the vertical velocity related with it falling down?
No, on the horizontal velocity.
Okay.
You know that the cart is moving at a constant velocity, so the net force acting on it is zero, but we control the apple as long as we use our hands, the air resistance applies a force on the negative direction of the motion, so the velocity of the apple will decrease, so it will fall.
So there are basically two kinds of explanations that I hear. One is there will be air friction, and hence the air friction will push it in the backward direction, so that the horizontal velocity will decelerate, and hence it will fall behind me. The other explanation is that just air friction is not relevant. So which one do you think?
sabit kalacak cismin ama biz hızlandığımızda hızımız arttığında zaten gerimize düşüyoruz. Hava sürtünmesi...
No, we are not accelerating. We are not going faster. We are moving at constant velocity. The cart is moving at constant velocity.
O zaman hani gerinin düşmesine sebep olan tek şey hava sürtünmesi oldu. Çünkü hızını azaltacak efendim.
Okay. Anybody else? So your answer is B? No, C. So your friend's example is a skateboard. If you are using a skateboard, if you want to jump over something which is hollow below, let's say, so you just jump upward, the skateboard continues, you keep moving in the same direction, and then you land on your skateboard. So your answer is C, or what's your answer? B and C. B just tells me that if you are throwing it upward, it will fall somewhere over there. That is B. A tells me if I throw it upward, of course I'm moving in the forward direction. A tells me it will fall somewhere over there. And C tells me it will fall here. So you are saying B. Okay.
Sürtünmesi varsa biz konstant speed'de gidiyorsak bizim üstümüzde bir güç var. Yani bir kuvvet var zaten. Bu elmayı tuttuğumuz için bu kuvvetimiz elmaya dökülüyoruz aslında. Elmayı attığımız zaman havaya bu kuvveti elmanın üstünden kestiğimiz için bizim hala üstümüzde kuvvet var. Orada fark ediyor.
Okay. First of all, is there a net force acting on us? Why yes, why no? Why yes?
Hava sürtünmesi olduğu için onu dengeleyecek kuvvet olması lazım. Yoksa net kuvvet geri doğru olacaktır, bir yavaşlayacak.
Okay. Why no?
Because there is no acceleration.
Well, in fact, you are both saying the same thing. The net force is zero. Of course, there is another force. To balance, as you said, the air friction, the sum should be zero. Okay, let's discuss a bit the Newton's laws, the force concept, etc. Now, here, for example, one thing you could have done was just go to another reference frame. Okay, the question told you, had given you a one reference frame, but you can just switch to another reference frame. Go to a reference frame in which is fixed with cart. The cart moves at constant velocity, so assuming the Earth is an inertial reference frame, that is still an inertial reference frame. So your reference frame is moving with the cart. So with respect to this new reference frame, the cart is not moving. The cart is at rest. What happens is there is wind pointing backwards. When you throw the apple, there will be a force due to the wind pointing backwards. The apple will not decelerate, or it will not gain, its velocity will not be negative. The velocity of an object cannot be negative. The velocity is a vector, it only has a direction. The components can be positive or negative. So I throw the apple, there is a force in this direction, and so there will be an acceleration in that direction. So the apple will accelerate in that direction. I'm at rest. The apple will accelerate in that direction. Of course, there's also the gravity. It will be doing a projectile motion with an additional force in the backward direction. Any more questions? Any more questions on this one? So it will fall behind me, but that is mainly because of the air resistance. If there were no air resistance in this new reference frame, if I throw it upward, the only force will be the gravitational force, which is in the vertical direction. So the horizontal velocity will not change, And since the horizontal velocity was initially 0, it will always stay 0. There will not be any horizontal motion, so it will fall right at my position if there is no air resistance. Only in that case. Air resistance is always there, but you see, in the reference frame fixed on the card, you see, in the reference frame, let's just imagine we do this experiment in the class. There is no wind in the classroom, in the reference frame fixed on the floor of the class. But if you go to our reference frame, which is moving at constant velocity, there will be a wind in this new reference frame. And if due to that wind, there will be resistance in the new reference frame, which is the reason why the apple will just move in the backward direction, in the direction of the wind. Yes, we are moving to a reference frame in which air is not at rest. Okay, so we were discussing the 3 laws of Newton. The first law was basically defining the inertial reference frames. The second law was telling us the relation between force, mass, and acceleration. And the third law was the action-reaction pair. Now, do you have any questions about it? I mean, you had many questions in your pre-reports. By the way, your pre-report for Chapter 4 have been graded. So just look at the notes also. I mean, if, for example, some of you, I didn't accept your pre-reports, I wrote the reason why I didn't accept it in the notes on your pre-report. And some of you, although I accepted it, there was a warning that if you don't ask any questions in your pre-report, I will not accept it in the future. Okay, so let's start with the second one. Now, one thing is, okay, if this is satisfied, this doesn't mean that m is equal to f over a. This doesn't imply this one. So one problem with this expression is that, well, we talked about the vector addition, subtraction, we talked about vector multiplication, but we didn't talk about vector division. It doesn't exist. So there's no vector division. This is one problem with this expression. Now, okay, so even if there is no, we can just correct it a bit. We can say that m is equal to the ratio of the magnitudes. You see, this does imply that the magnitude of force divided by the mass is equal to the acceleration. But even this one doesn't mean that the mass is equal to force over acceleration. Especially in one case, if there is no acceleration, how do you divide by 0? So this is the reason why this law is written in this form, but not this one. What you can say is, if the magnitude of force divided by the mass m is equal to the acceleration, this does imply the mass is equal to f over a if a is not 0. Okay, you will see lots of these things in your calculus courses or in your future mathematics courses, but this is a point where you should pay attention to, because otherwise you can get some weird answers, questions like, what happens if a is equal to 0? How do we define the mass? Well, this question arises because you are not paying attention to the fact that this is valid only if acceleration is non-zero. But this is always valid even if the acceleration is 0. Now, another problem is the action-reaction pairs. If you remember what the law was, it tells us that if you exert a force on something else, that something else is exerting exactly the same force on you. For example, if you are pushing your friend with, let's say, 40 newtons, the unit of force is equal to the unit of mass times the unit of acceleration, which is, well, the unit of mass is kilograms, the acceleration is meters per second squared, and this combination is defined as Newton. So let's assume that you are pushing your friend with 20 newtons. But in everyday life, what we do is, what we say is, you are pushing your friend with some force, but your friend is not pushing back. That is not possible. If you are pushing your friend with 40 newtons, your friend is pushing you with 40 newtons also. Unless there is a resistance by your friend, you cannot push him by 40 newtons. So if you want to exert a force on anything, that thing has to resist the motion. Otherwise, you cannot exert a force. It's not something that you cannot just decide to exert like 90 newtons on air. You cannot do that. Or 90 newtons on paper. You can only exert a force if there is resistance. And when there is resistance, basically the object you are exerting a force is also exerting a force on you, and the two magnitudes are equal. Now then, of course, there is a question. Let's just take one of these homework. Let's just move your hand. What is the force that I'm exerting until this point? 0, basically, ignoring air friction. I hit this one. Well, the motion of the paper changed significantly, but the motion of my hand didn't change at all. Or you can just imagine that you are just moving in a car and the fly just hits the windshield of your car. The fly is killed, and, well, you just start the wipers to clean your screen, and you don't feel anything. So if you both exert the same force, the force that you have exerted on the fly is exactly the same as the force that the fly exerted on you. So why is the difference? Why does the fly die whereas nothing happens to you? Or in this example, why does the paper move? It changes its motion drastically, but I don't change. The motion of my hand is basically not affected.
Because of their mass difference?
So?
In the example of the fly, the mass of the fly is almost non-existent compared to car. So the fly changes its velocity and has an acceleration during the time of the impact, but the acceleration change in the car is negligible.
So how does the acceleration cause the fly to die? Cause the death of the fly? Or let's do an example of an egg. You just hit an egg with a heavy object, the egg breaks. So how is the acceleration related with the braking? So your answer is correct in the sense that although they are exerting same forces, the masses are so different that there will be different accelerations. But still there is one step missing. We have to relate the acceleration of the object to the breaking of the egg. So why does one thing break whereas the other one doesn't? If they are under the influence of the same force, or if they have the same acceleration. Under the same force, different acceleration. If the acceleration is big enough for an object that has a very small mass, why does it cause it to break?
Lesser density, since the object with lesser mass and lesser density, particles not exactly particles, but it sort of breaks more easily than compared to the car, which has no damage. It sort of absorbs the shock.
Okay, I will still ask the question: what do you mean by absorbing the shock, and how is the density related? You see, there is There was some news a couple of days ago in New Scientist. They were saying that they had built the lightest metal. Now you can just hold it on top of cotton, let's say. It's so soft, it's so light. Nevertheless, it's quite strong. Although its density is very low, it doesn't break. Okay, we didn't yet discuss the momentum. How is I will ask you, if you tell me momentum, I will tell you how is momentum related to the braking.
We are holding an egg, and let's assume we are using a spoon. When we hit the spoon to egg, spoon is trying to move the egg, but since we are holding the egg, it won't move. So if it tries to move, as a result, it can add this stress.
What do you mean stress?
I mean, we are holding the egg and we are trying to move the egg. If we are holding the egg as a way that it won't move, it can't. It's a dilemma.
There's no dilemma.
No, it's not a dilemma, but there is stress. It's called stress on egg.
What's stress? Okay, let's do an example before we continue discussing with this problem, which will be some kind of an application of what we had learned about the Newton's law. Let's just assume that this is the wall. We attach a mass to the wall with a string. Let's call the mass M. So first of all, now you can just imagine here is our mass. May I use this? Okay, may I use this, wherever it belongs to? Okay, this is our mass. So we are just hanging it from the ceiling. Okay, this is the system that we are imagining. So does it accelerate? Relative to the reference frame fixed on Earth. Does that mass or does this mass accelerate? Earth is inertial, that's what we will assume. Earth is inertial. No. Okay, it's not accelerating. Its velocity, initial velocity is 0, its final velocity, its velocity will always stay 0. So acceleration is 0. Now what is the net force acting on it? Well, Newton's second law, the force is equal to mass times acceleration. It's again 0. So, what are the forces acting on it? Well, there is the tension. There is also the weight. Now, weight we didn't yet discuss, but basically we already know that weight. So we had already discussed that if you throw an object at any direction, it will have a constant acceleration. Close to the surface of the Earth, it will have a constant acceleration, whose magnitude is equal to g. By the way, I'm not writing that acceleration is equal to minus g or acceleration is equal to g, because g is just a number. It stands for 9.8 meters per second squared. It cannot be a vector. So it's just the magnitude of the acceleration, which is g. So that, according to, again, Newton's second law, there has to be a force acting on it, which is its mass times its acceleration. This is what we call the weight of the object, or the magnitude of this thing is what we call the weight of the object. So the weight of any object is just its mass times g pointing in the downward direction. So you see, here there is already the weight pointing downward. But the net force is 0, so there has to be something balancing it, and that thing is created by this string. So this is what we call the tension force, the force exerted by a string on the object that it is attached to. Well, let's choose some our coordinate axis. Let's just choose this direction to be the z direction. Then the weight of the weight vector is well, its magnitude is mg, that we know. Which direction it's pointing at? It's pointing in the minus z direction. The tension force, well, it should be, let's say, T in the z direction. The net force is nothing but omega plus T. You see, I'm not subtracting that. The net force is always vectorial sum of the forces acting on objects. Although I know that they are pointing in opposite directions, but the vectors already take care of the directions themselves. So I'm not saying it is T minus omega or omega minus T. It's always, the net force is always the sum of the forces. But of course, one of the forces, omega, is in the minus z direction. So if we write it in terms of the components, mg z hat plus T in the z hat, so the net force is equal to T minus mg in the z direction. And this is equal to, this should be equal to 0 because the object is not accelerated. And from here, we know that the tension force is equal to mg. At least in this case, this is what the tension force is equal to the weight. Only in this case, by the way. In general, it will not be equal to the weight. But in this case, since the only forces acting are the weight and the tension, and the object is not accelerating, the tension has to be equal to mg. Now, of course, there is a problem. What creates this tension? Okay, from a macroscopic point of view, we have the string made up of, it's a continuous matter. So we just say that there has to be some such a force acting by the string on the mass. But what creates this tension is basically the chemical bonds between the atoms making the string, the chemical and physical bonds. So it's again a force that is created by, at the fundamental level, their electromagnetic interactions. Now there is a maximum amount of tension that any material can support. If you take a string, if you stretch it too far with a large force, it will just break eventually. There is a maximum tension. So if the mass is large enough, the string will not be able to provide enough tension, so the string just breaks. Now let's go back. Well, this is also one of the so-called, you can treat the tension in a string as kind of an internal force also. So if you just take the string, take this string, any string, let's say you exert a force in this direction here, another force in the opposite direction on the other side. Now if you just imagine one part of this string, take this small part. It is at rest, the string is at rest. Let's assume it is massless. But if it is, let's just assume it is massless. It doesn't have to be at rest. What is the force acting on the string if it is massless? F is equal to m times a, that should be equal to 0. So if you take a small part of the string, it will be 0. So you see, let's just choose a horizontal direction. This is our x. So let's call F is equal to F in the x direction, F prime is equal to f prime in the minus x direction, f total, which is f minus f prime in the x direction, this should be 0. So the forces at both ends should be equal in magnitude. Of course, they are pointing in opposite directions, but their magnitude should be equal. Now let's assume not this one, this part, but this part of the string. What is the net force acting on this part of the string? It should be again 0 because the mass of only this portion of the string is 0. So m is 0. The net force should be 0. So there are two forces. There is this force acting on this one. There should be another force acting on this segment to keep the net force 0. And that is the force exerted by the other part of the string. So there should be a force. Let's call this one F double prime. F double prime should be equal to minus its magnitude x hat, and F double prime should be equal to F prime. And in fact, this happens for any segment that you can imagine. If you take any segment of the string, there will be forces at both ends of the string pointing in opposite directions. They will all have the same magnitude, and this magnitude is what we call the tension. Tension is not a vector. Tension is a scalar quantity. It's just this number. It's this magnitude. But tension creates a force acting on objects. And the direction is always parallel to your string. And, well, you just need to determine it from case to case. For example, in this problem, if you look at this segment, the force created by tension on this segment is pointing in that direction to balance the net force. If you look at the other segment, the force acting on this orange segment will be just pointing on the other direction, just to balance the total force. Okay, any questions on tension? Yes.
Can't we say F and F prime can be different?
Well, we just proved that they cannot be different F and F prime if the string is massless. You cannot exert different forces. You cannot pull one end of the string by 5 newtons and the other end of the string by 10 newtons. You just cannot do it.
If it had some mass, then how could it be different?
Let's discuss that example in the next hour. We will assume a finite mass string and we will see how it will be different. Now, this one I will be relating to. Now, before you go for a break, let's just imagine some egg. This is our egg. Now, although it's a large object, Newton's laws are not really applicable to an egg, in the sense that Newton's laws are valid only to point objects. We cannot just apply Newton's law to an egg in a straightforward manner. Of course, Newton's laws are still valid for point objects. And if an object is not changing its shape, in that case, we can still treat it as a point object. But if it starts to change its shape, then it's no longer a point object. But what we can still do is we can divide this egg into very small point-like objects. We can assume that, okay, the egg, we can divide it into small parts. Each part of this egg is very small, almost like a point. They do not change their shape. So we can apply the Newton's laws to each one of these very small parts of the egg. Now what will happen is, okay, there is an external force we exert, let's say, on this part. We are exerting a force on this part. We can just take a needle, push it on that part, or if you hit it with a very solid spoon, let's say, since it's round, the spoon is almost flat, it will most probably touch the egg at a very small part, initially at least. But we know that the egg is solid. Different parts tend to move together. So even if you just, without breaking it, hold the egg. When you hold the egg, you are exerting a force, let's say, over here. You are holding this one. I am exerting a force only here at the bottom, not at the top. But as the object is moving, even the top parts are also accelerating. They are accelerating because there are certain forces inside the egg which connects this part to the other part, which connects to the next part. They can be modeled just like strings. You can imagine there are strings connecting various parts of the egg to each other. When you push one of the parts, the other strings exert forces on the other parts. So it causes the other parts to accelerate. But the strings have a finite maximum tension that they can support. So if you exert if you take a string, exert a larger and larger force, there will be a point in which the tension will be so big that you cannot create such a tension on the string. It will break. Well, the same thing happens over here. If you try to accelerate this part much faster than what these internal forces can accelerate the other parts, what will happen is this will just move faster and faster. Well, eventually the tension in the strings connecting various parts of the egg should be so large that you cannot create such a large tension. And since it cannot support such a large tension, the strings connecting different parts will just break. And you cannot just move the egg will no longer stay as one object. It will just break down. This is why it's basically the reason why an object breaks or why a fly that hits your windshield dies is mainly different parts of the object tries to accelerate at different acceleration, have different acceleration, because there are different forces accelerating each one of them. Internal forces will not be strong enough to accelerate all the other parts with the same acceleration. So their relative position will change, and if you just change their relative position beyond a certain limit, things just break down. Okay, any questions? This one, what do you mean by balance? It can be accelerated. The only assumption I made is that the string is massless. Okay, see you after the break.